एक्सक्यूज मी सर।
यस बोलो।
सर एक्चुअली सर मतलब पिछले कुछ क्लासेस में मैं फॉलो ढंग से कर नहीं पा रहा था क्योंकि मतलब थोड़ा हेल्थ खराब था। तो बस एक बार
क्या
कुछ
हो
टॉपिक
गया?
बोल दीजिए कि सर थोड़ा बीमारी टाइप चल रही थी, वीकनेस टाइप।
अच्छा,
सर तो एक बार बोल दीजिए कि कौन कौन से टॉपिक पढ़ना है मेरे को, मतलब आज तक आने के लिए।
तो अभी हमने एक्चुअली पिछली क्लास का कुछ, यू वर देयर ना पिछली क्लास में कि नहीं?
हाँ, आई वाज देयर बट आई वाज नॉट एबल टू फॉलो। मतलब मैं
अच्छा
फोकस ही नहीं कर पा रहा था ढंग से।
अच्छा, तो ये जो हमने जो टॉपिक है ना, ये तो हमने इस पे पोस्ट कर दिए हैं सारे, जो हमने किया कवर।
ओके ओके ठीक है, ओके ओके सर।
ठीक है ना? तो एक्चुअली अभी इसमें क्या है ना, हम अभी इंटीजर मल्टीप्लिकेशन देख रहे हैं, इंटीजर मल्टीप्लिकेशन की एल्गोरिथम और उसकी कॉम्प्लेक्सिटी। तो
ओके
पिछली क्लास में हमने देखी थी जिसकी कॉम्प्लेक्सिटी ऑर्डर ऑफ एन रेज़ पावर 1.58 समथिंग थी। ठीक है।
राइट राइट राइट।
और आज हम देखेंगे कि कैसे इसको इम्प्रूव कर सकते हैं, तो वो हम बताने वाले हैं बेसिकली। ठीक
ओके
है।
राइट राइट
और आई थिंक आई विल ट्राई टू पुट सम मटेरियल सो दैट यू कैन रीड ऑल्सो सम रीडिंग मटेरियल। ठीक है।
राइट सर।
ठीक है। सो ओके, सो मे बी आई शुड स्टार्ट नाउ एक्चुअली। Can you see the screen now?
यस सर।
Okay. So I think we were about to discuss this college test algorithm for multiplying two integers. So last class I just gave you a brief idea. So what we do, we split two numbers a and b, two integers into n blocks. So say a could be a0 plus a1b plus dot 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 a n minus 1 b raised to n minus 1, where capital B is the base. And similarly, we can write down b, okay, where these ai's and bi's are elements from 0 to b minus 1. Then we actually write down the corresponding polynomials. So we can write down f of x with these coefficients as ai's and g of x with coefficients as bi's. These are two degree n minus 1 polynomials. Then what we do? We find out a product polynomial h of degree 2n minus 2. Okay. And there we call the coefficients as ci. We can compute the values of ci actually. And then we evaluate h at base b. And that is what will be the product actually. Okay. So what we do normally, we evaluate f and g at two endpoints, x0, x1, x2 and minus 1. In the previous algorithm also we have done the similar way. So now actually then we evaluate, so we know f of xi, we know g of xi, so we'll get h of xi. Normally we take in this algorithm special choice for xi as omega raised to power I, where omega is a primitive 2 and nth root of unity. Okay, so that means omega is something like e raised to power pi I by n. So this is the basic algorithm. So how do we actually achieve this? So what we are going to do, we are going to use uh, fast Fourier transform to compute this, and the algorithm turns out to be with complexity n log n log log n. Okay, so let me explain this algorithm to you. So some of these things you may be knowing actually, but okay. So I think this is lecture 5. So I am going to first describe discrete Fourier transform. Okay, and suppose n is a integer greater than or equal to 1, and write down omega as e raised to power 2 pi I by n. It's a nth root of unity. In the actual algorithm, we use 2nth root of unity, but just for the illustration, I'm giving you everything in general. Omega is e raised to power 2 pi I by n. So we can define discrete Fourier transform of a vector. So suppose u is equal to u0 u1 un minus 1 is a vector in Cn. C is a field of complex number, right? We apply the discrete Fourier transform here. So discrete Fourier transform is another vector u hat with each component as hat, u naught hat, u1 hat, and so on, un minus 1 hat. Okay, this is also belongs to Cn, where each typical hat uk, so 0 less than equal to k less than equal to n minus 1, is given as summation uj omega raised to power jk, k is equal to 0 to n minus 1. Okay, so this is the general discrete Fourier transform. So given a vector like this, u a hat is given. So each component u0 is given by this expression, u1 is given by this expression. This is known as discrete Fourier transform. Let us take an example. Let us take a quick example. N is equal to 4. So that means our vector u is u0, u1, u2, u3. Okay. So then we have u naught hat, the first component, u0 plus u1 plus u2 plus u3. u1 hat is u0 plus I times u1 minus u2 minus I times u3. u2 hat u0 minus u1 plus u2 minus u3. So this is, for example, I square, I, I cube and so on, so the value is plus minus I. And then finally u3 hat is equal to u0 minus I times u1 minus u2 plus I times u3. Okay. So that this is the discrete Fourier transform. If vector is u0, u1, u2, u3, the four components are given like this. So as you can observe here, let me take some more space here. As you can observe here, each component here is nothing but a polynomial, right? Right now, it's a polynomial in the coefficients ui's, right? It's a polynomial evaluated at omega. Omega is a, nth root of unity. So we can write down in a much better definition, I mean, in terms of polynomial. So let me write it down. So we can write down equivalently that discrete Fourier transform evaluates a polynomial at the nth roots of unity So if polynomial is f of x is equal to u0 plus u1x plus dot 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 un minus 1 x raised to power n minus 1, then u hat is nothing but f of 1 comma f of omega comma f of omega square. This is another way of writing the discrete Fourier transform. Okay, so you can see that these polynomial evaluations are given here. Okay, because these are nothing but the polynomial evaluated at omega. Okay, different powers of omega basically. Okay, so essentially this f of x lives in the quotient ring cx modulo x raised to power n minus 1. Okay, so in this case discrete Fourier transform explicitly evaluates the isomorphism have Cx modulo x raised to n minus 1 goes to direct sum k is equal to 0 to n minus 1 Cx modulo x minus omega raised to power k. Okay, this is another way of looking the discrete Fourier transform. Now the question is actually what is the complexity of discrete Fourier transform? If I want to compute the complexity of the DFT. So in the normal ways, or in I would say naive ways, it takes order of n square operations. Okay, operations. So here these operations are algebraic operations, addition and multiplication, etc. in C. That's what we need to do. Okay. So its complexity is order of n square. Why? Because we have n coefficients, and we everything is multiplied with and then we are actually computing evaluating. So basically we are taking the addition and so n into n is n square actually. But actually the question is now, can we do it better? So the answer is yes, and I think you might be knowing this. That there is an algorithm known as, sorry, 1 minute. There seems to be some problem here. Okay, that's good. Okay, so we have the algorithm fast Fourier transform FFT, that does it in order of n log n. And how it does it, you remember, I think that we have to use the divide and conquer approach to compute the FFT. So normally it assumes that n is a power of 2, and then we try to compute the recursively we compute this fast Fourier transform. So I think right now I'm not going to the details of that algorithm, but we know that that can be done in order of n log n. I can give you some reading material which you can actually look at it for this. Okay. Now, so the FFT can be used to quickly multiply polynomials. Can be used to quickly multiply polynomials. So how do we do this? The basic architecture is given polynomials f and g in Cx of degree less than n. First, use FFT to evaluate f and g at the nth roots of unity. Okay. So first thing, use FFT to evaluate f and g at the nth root of unity. Second, multiply their values at these points. Okay, so given two polynomials f and g, okay, we look at the polynomial coefficients basically, right? So basically, you know that they're kind of vector, right? Anyway, you use FFT to evaluate f and g at these nth roots of unity, so you'll get these points. Multiply these values at these points. Now third is use inverse FFT to interpolate at the nth roots of unity. Okay, so output is the product fx into gx modulo x raised to power n minus 1. In fact, this is nothing but what is known as cyclic convolution of length n. So actually this language of cyclic convolution is used by digital signal processing guys, the people who work in signal processing, they use quite a lot. So let me define what is convolution actually. So what is convolution? We can do all this in a more general settings. Suppose R is a ring. We assume it is a commutative ring with identity. Okay. Suppose f is a polynomial a0 plus a1x plus an minus 1 x raised to power n minus 1. Okay. And g is b0 plus b1x plus dot 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 bn minus 1 x raised to power n minus 1. So f and g are two polynomials of degree less than n. So both of them have degree less than n in Rx. Two polynomials in Rx. R is a ring with unity. Then we can define convolution of f and g as f star ng. We can define it as summation k is equal to 0 to n minus 1 ck x raised to power k. So what are these coefficients ck? I can write it down. Summation k is equal to 0 to n summation over I comma j, where I plus j is equal to k mod n ai bj x raised to power k. This is how we define convolution of two polynomials, f and g. So let me give you an example here. Suppose f is 1 plus x square is a polynomial in integer modulo x, and g is another polynomial 2 minus x, again in integer modulo x. So we know that the product of two polynomials fg is nothing but, you can just multiply component wise. You have 2 plus x square minus x cube. Okay, and the convolution of f and g is 2 minus 1. Using this formula, I am just applying this formula. 2 minus 1 plus 1 into x plus 1 into x square. And this turns out to be 1 plus x cube. Okay. So this is the convolution of these two polynomials. In particular, I should say that we have a result. If degree of f is less than n and degree of g is less than n, then we can consider them as polynomials of degree less than 2n minus 1. In other words, we can do this by setting the other coefficient 0, by setting an is equal to dot 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 a 2n minus 1 is equal to bn is equal to dot 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 b 2n minus 1 is equal to 0. All other coefficients are 0, then we can assume that they are polynomials of degree less than 2n minus 1. In this case, we have f star 2ng, is basically f dot g. This is the result. And also, I just want to mention that whatever interpolation we computed, in general, f star and g is nothing but, this is 2n, you remember this is ng, is f dot g mod x raised to power n minus 1. That's another result that I would like to mention. So here you can see that this result is true. So x cube is equal to 1 here, right? X cube minus 1 modulo, we can take x cube minus 1 actually. Okay, now we have a lemma. Suppose for n to be a natural number, okay, suppose there exists a primitive nth root of unity omega in R. R is a ring, actually we are assuming a ring with identity element, commutative ring with identity element. Now for any two polynomials, f and g in Rx of degree less than n, we have discrete Fourier transform we call it with respect to W of f star and g. The convolution is same thing as discrete Fourier transform with respect to omega of f times discrete Fourier transform with respect to omega of g. In other words, this is written as f1 dot g1 comma f omega dot g omega dot 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 f of omega raised to power n minus 1 times g of omega raised to power n minus 1. Okay, so when we take two polynomials f and g, we convolute them, okay, convolution of order n, and take the discrete Fourier transform. It is nothing but the product of the discrete Fourier transform of the individual polynomials f and g. This is a basic result, and I think we can try to prove it also. So you know that the convolutional polynomials, there exists a quotient polynomial q in Rx such that the convolution can be written as f dot g plus q times x raised to n minus 1. So we can actually evaluate f star n g at a typical power of omega. This will be f g omega I plus q of omega I then omega I raised to power n minus 1. This is f of omega I dot g of omega I plus q of omega I. This I can interchange. This is omega raised to power I raised to power n. So I can write it down as omega raised to power n raised to power I minus 1. This is nothing but f of omega raised to power I g of omega raised to power I plus q of omega raised to power I. Now omega raised to n is omega is a nth root of unity, so omega raised to power n is equal to 1. So this is 1 raised to power I minus 1. So this is 0 actually. So basically we are left with f of omega raised to power I times g of omega raised to power I, and that is a proof, right? So basically because so each component is like f of omega raised to power I dot g of omega raised to power I. So discrete Fourier transform of the convolution is given like product. Okay. So I should just want to mention here a side note that in college stress and algorithm actually we compute discrete Fourier transform of omega with respect to f and DFT with respect to omega of g, where omega is 2nth root of unity. This is the key difference. I have given you the algorithm in general, but in that case, we take omega to be the 2nth root of unity. Okay. So now basically f star and g is equal to f dot g. I can write it down as polynomial h. I is equal to 0 to 2n minus 2. If you remember, c of I times x is for I. So there we have the discrete Fourier transform of omega of h is equal to dft of f dot g omega is equal to dft of f star and g is equal to the product separately. Okay. So I call this equation 1 here. I need some more space here now. Okay, so this is the thing. Any question up to this point?
No, sir.
Okay, so now I think now the rest of things are pretty straightforward. Let me write it down. Note that 1 minute. Note that discrete Fourier transform. Oh, sorry, this is discrete Fourier transform omega is actually also given by the following matrix, following Vandermonde matrix, you know. V omega, random mode of 1 omega, omega raised to power n minus 1. So essentially this is nothing but 1 1 1 1 1 omega square and so on, omega raised to power n minus 1. Finally 1 omega raised to power n minus 1 and so on, omega raised to power n times n minus 1. This is the matrix. Okay, Vandermonde matrix. So the coefficient vector A is equal to A0 an minus 1 transpose of a polynomial f is equal to summation I is equal to 0 to n minus 1 ai exists for I in Rx. If f is a polynomial with coefficient vector ai, the coefficient vector is mapped to a vector v, which is f of 1, f of omega raised to power n minus 1 transpose. You can write it down as v omega dot a, and vice versa. Okay, so basically a is nothing but v omega inverse dot v. So we have the following theorem actually, which I should mention here without proof. Suppose so omega is a primitive nth root of unity in R. Then omega raised to power n minus 1 is nothing but omega inverse is also primitive nth root of unity. Nth root of unity. So actually, if one element is primitive, its inverse is also primitive. This is the result. So in this case, we have v omega inverse is equal to n times in. Okay. So now actually using this theorem, we can apply in this equation 1. If we can apply the discrete Fourier transform inverse, omega inverse to both sides. Okay, so what we can get, apply DFT omega inverse to both sides of 1 of equation 1. So then we will have, so basically the coefficient vector C is equal to C0 Cn minus 1 transpose of the product polynomial h is equal to summation Ci x raised to power I is equal to 0 to n minus 1 will be n times C is equal to DFT omega inverse of DFT omega h is equal to DFT omega inverse of DFT omega of f times DFT omega of g. Okay, so we are applying the inverse Fourier transform, Fourier transform, basically DFT inverse, and then we get n times c. C is the polynomial vector here. Okay, So in fact, using the fast Fourier transform, we have a fast convolution algorithm, which I can write it down now. So input is a commutative ring, capital R, two polynomials f and g in Rx of degree less than n is power of 2, k is a positive integer, and omega is a primitive nth root of unity. Okay, so output is convolution of two polynomials f star and g. So first thing, compute, what we compute, omega inverse as omega raised to power n minus 1. Third, df stands for discrete Fourier transform with respect to omega of f polynomial, and dg stands for discrete Fourier transform with respect to omega of g. Okay. Fourth, dh, which is the product of df and dg. Okay. And fifth, we can compute this e, which is dft omega inverse of dh divided by n, because the n component was there, right? So answer is written E. So now we know that this convolution can be done. So I think I can write down as a summarize as a theorem. If f and g are two polynomials in Rx of degree less than n is equal to 2 raised to power k, k is positive integer, and we know that omega is a primitive nth root of unity. Okay. Then the above algorithm algo computes the convolution f star n g using order of n log n arithmetic operations. Okay. So this is the key thing. So essentially, so you got the idea. We compute the basically, so product can be computed in actually, once we have this thing in n log n, I can write down another theorem. F and G are in integer modulo x of degree less than n. Then f dot g can be computed using order of n log n times m log n. M log n is a multiplication of 2, and this we can apply recursively, so this will be order of n log n log n m log n m log n and so on actually, so this is the complexity that you can get for computing. So essentially, fast Fourier transform is computing things in n log n, right? And the convolution, because that's why we are able to compute the convolution in n log n, right? So this is the key idea behind the algorithm. So do you have any questions so that we can answer anything? One thing I think that you can try to do is this theorem here, which I have written, I think without proof, but is 1 minute. This is the convolution. Yeah, this result. You may want to prove this result. It is not very difficult actually, but if you can prove it, that would be nice. Okay, any question? I think people are there.
No, sir, no questions.
So have you seen this material before or not?
Yes, sir. Yes, sir.
Where?
सर एक्चुअली फूरियर ट्रांसफॉर्म हमारे फर्स्ट सेमेस्टर में पढ़ाया गया था एल्गोरिथम्स में.
अच्छा, उसकी कॉम्प्लेक्सिटी भी पढ़ाई गई थी.
हाँ, मतलब हमको असाइनमेंट में दिया गया था कि कॉम्प्लेक्सिटी खोज के लाओ, तो फिर थोड़ा बहुत आइडिया है एक तरह से.
ओके ओके फाइन. तो ये थोड़ा सा मेरे को जानना है कि तुम लोगों को क्या आता है, तो अकॉर्डिंगली आई कैन स्किप समथिंग, अदरवाइज बट एनीवे. So I hope so. Should I give you? So now I think maybe I can put some reading material, for this algorithm. Okay. So
Yes, sir.
ठीक है. I think so. That's all for today. I think I'm not going to discuss anything more here. Okay. So next class we'll be doing something else. Okay.
Okay, sir.
So next class is on Friday, right? 2 o'clock. Yeah. Okay.
सर वैसे मिड सेम वगैरह कब होगा?
मिड सम आई थिंक वैसे तो इन लोगों का कुछ मार्च कह रहे फरवरी 27 के आसपास है ना. तो बट आई एम नॉट श्योर एक्चुअली वी शुड डू इट एट दैट पॉइंट ऑफ टाइम, बिकॉज हमारे पास अभी कुछ तब तक कितना मटेरियल कवर होता है वो हमको देखना पड़ेगा, राइट? Because there are only 4 people now. I think it is freeze now, so we know only there are 4 people, so we can plan something, not an issue. Okay.
Yes,
or
sir. Yes.
We can be do certain things which may be useful. Okay, so not an issue. Okay, we can do something. Okay.
ओके सर, प्लीज थोड़ा फूरियर ट्रांसफॉर्म का थोड़ा कुछ मटेरियल डाल दीजिए आप ऑनलाइन.
हाँ, मैं डाल दूंगा, श्योर.
ओके,
तो मैं एक्चुअली इस पेपर का ओरिजिनल पेपर का रेफरेंस भी डाल दूंगा, सो दैट यू नो एग्जैक्टली क्या है. ठीक है. ओके,
राइट सर. Sir, can we leave the meeting?
हाँ, sure. I'm just sending it. Right, 1 minute.
Okay, right, sir.
आशीष होस्ट किया.
सर ने लीव कर दिया एंड करने की जगह. चलो ठीक है.
सर को मुझे लगता है ये लगा कि सर आप कब लीव करोगे, मुझे ऐसा लगा जैसे.
हाँ, सर ने कहा था मीटिंग एंड कर रहे हैं, पर मीटिंग एंड नहीं किया, हुआ नहीं मतलब.
पता नहीं है.
चलो बढ़िया, खाना वाना खा लो.
वही जाओ खाना वाना.
ठीक है, बाय.
ठीक है. बाय.